Why care about the imaginary numbers? After all, we live in the real world. Stop spending your time living in a dream and give up hope on the complex numbers. These are sentiments that you may have heard before. And if that's you, if people are just hating on you for wanting to learn the complex numbers, and you're just constantly going through this rain cloud and this barrage of attacks because of your decision to stray beyond the real numbers. Let me just tell you what you can say, why the complex numbers are important. So, first of all, think about the negative numbers, okay? Why are the negative numbers important? Nobody ever has had negative 12 apples in their life. Maybe they owed their friend 12 apples, but that's not the same as having negative 12 apples. They didn't literally have these 12 objects which were like anti-apples that then they could give to their that somehow they needed an apple to like destroy. That doesn't make any sense, right? So negative numbers are just an abstract idea. They're not a real physical quantity. They're not counting numbers that exist. However, let me give you a different way to think of the negative numbers. They're not just these anti-particles that destroy the natural numbers, the particles of the natural numbers, okay? Negative numbers are a mirror. The number zero is a mirror, okay? The number zero is a mirror, and the negative numbers are a reflection of the real numbers across the mirror of zero, okay? And we can see that in multiplication. So in addition, negative numbers behave like, if you add a negative number to a positive number, it just behaves like subtraction, right? But for multiplication, if you multiply, let's say 3 by negative 2, that's going to amount to multiplying 3 by 2 in the traditional sense, and then reflecting that result across the number 0. Okay, so you're going to do 3 times 2, you get 6, and then reflect that across the number 0, and you get negative 6. Now, reflections are critically important to our understanding of the world, and reflections, in fact, were built with a reflectional symmetry, a reflectional symmetry across this axis. Human beings have this reflectional symmetry, and they've evolved it. And reflections across an axis can also be thought of as a 180-degree rotation, right? If I start here and I reflect across the number 0, that's the same thing as if I was sitting in the plane and I rotated by 180 degrees. So if we allow ourselves to include other rotations, such as a 90-degree rotation, so that if I do a 90-degree rotation, then I'm sitting at the vertical position up in the plane. That's the number I, okay? That's the imaginary number, okay? So the complex numbers just allow our multiplication structure to take on arbitrary degrees of rotation instead of just the 180-degree reflection encoded by the negative numbers. And this is why when you're solving the equation x squared is equal to 1, for instance, okay? So when you're solving the equation x squared is equal to 1, this has two solutions, 1 and negative 1, right? If I multiply 1 by itself, I get 1, and if I multiply negative 1 twice, let's think about this geometrically, multiplying negative 1 times negative 1 is essentially starting at negative 1 and reflecting it across 0 to get back to positive 1. The point is that if you multiply a negative number by a negative number, that's two reflections, or that's two 180-degree rotations, which result in a net no change, so a net positive number, right? Ultimately, reflecting twice undoes the act of reflection. So reflecting twice is just the identity operation. It leaves the system unchanged. So therefore, any number, negative number, which is multiplied by another negative number is going to be positive, because that's two 180-degree rotations starting on the positive axis, boom, and then back, boom. And so if we want to end up with doing two rotations or two actions of multiplications to get to negative 1, say we want x squared is equal to negative 1, well, in order to do multiplication twice and get to negative 1, we need a 90-degree rotation. so that if I'm starting here at 1 and I want to get to -1, which is a 180-degree rotation, I just need to multiply by I, which rotates me by 90 degrees, and then multiply by I again, which rotates me by another 90 degrees. And so then I get to 180 degrees, okay? So complex numbers allow us our multiplication structure to include two-dimensional plane rotations. And namely, if I have an arbitrary complex number and I multiply, let's say I have two complex numbers and I multiply them together. So here's one of my complex numbers, and then my other complex number is, let's say, on my other eye here. So I have two complex numbers whose vectors point on each, the tips of the vectors on each of my eyes. Then if taking this complex vector and multiplying it by this complex vector, I essentially look at the angle of this complex vector and I look at its radius. And then I look at this number, I multiply the radius of this number by the radius of my other complex numbers. So their radiuses just multiply like normal real numbers, okay? Their radiuses just multiply like normal real numbers. And then with a rotation is basically, I take the angle of this vector, I basically rotate my vector by that angle. So I just rotate this vector by whatever angle the other vector is, okay? So basically the angles of the two complex numbers are just going to add together. So the radiuses multiply, the angles add. And that's our famous formula, r e to the I theta, right? A complex number can be written as r e to the I theta, where e to the I theta is encoding the angle of the complex number, so theta is the angle, and then r is the radius. So if I multiply two complex numbers together, then I just get r, the radiuses multiply, and then these e to the I thetas multiply, and the exponential, how it works is if you multiply two exponentials, the argument of the exponent will add, and so we get the angles add. And so we're adding up the angles of rotation in our multiplication structure. We're multiplying the radii. Okay? And so yeah, it's just a beautiful and powerful way to encode essentially two-dimensional rotations, and it's something called a Lie group structure. Okay? So we have this entire plane, which is a continuum, infinite amount of numbers, right? Like the entire complex plane. All of these imaginary numbers, there's an infinite amount of them. It's a two-dimensional plane, and there's a group structure on it. So there's this this structure of multiplication which encodes the symmetry of two-dimensional rotation. So it's actually called what's called a Lie group. Okay. Now, if you try to generalize this concept to three-dimensional rotations, okay, it turns out that there's no immediate way to do that, and in fact, you need to look at a four-dimensional number system called the quaternions to generalize this idea further. We're going to talk about the quaternions and the octonions in a more detailed and more rigorous video. But we're just sticking to the quaternions. You can just think of them colloquially as somehow encoding the geometry of three-dimensional rotations, but in a four-dimensional way. Okay. However, just sticking to the complex numbers for now, understanding two-dimensional plane rotations are critical in our understanding of everyday life, because every three-dimensional rotation is about some axis. So if I take a sphere and I rotate it, I need to pick an axis that I fix, and then I'll rotate that sphere about the axis. Okay, and these are represented by orthogonal matrices with positive determinant. Okay, so just for those of you who are more familiar with linear algebra, any rotation is going to be essentially a matrix with orthonormal columns. So it's an orthogonal matrix. It's going to have determinant 1, positive 1, okay? But for those of you who aren't as familiar, that's okay. Just think about any three-dimensional rotation. I have a fixed axis. I'm rotating about that fixed axis. And then what's actually getting rotated is the plane that's orthogonal to my axis of rotation. So clearly, plane rotations are going to be really important to three-dimensional rotations, as well as just, your bare bones two-dimensional rotation. So, and if we want to understand reality, we want to understand physics, well, we need to understand rotation, because rotation is a critical part of motion, okay? Rotation is one of the key qualities that we ascribe to motion, right? Angular momentum. We look at the center of mass in classical mechanics. We look at the center of mass of an object. But we also look at its angular momentum, right? Its angular momentum. So yeah, rotations are pretty important, and then you can just tell your friend if they said, "Oh, well, why do you care about the complex numbers? Why are you wasting your time with the complex numbers?" Just tell them to never rotate their head, never turn your head about an axis, never rotate anything anymore. Anytime you write on a piece of paper, you're not allowed to rotate it. You just have to keep it fixed in that location. And yeah, and then ask them, okay, now do you want to learn about the complex numbers? Now do you want to learn about rotation? Because rotations are pretty important. So, all right, y'all have a great day.